I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew, and I'm joined as always by my co-host Taylor at the University of Utah. Taylor, how's it going?
Life is good, man. So I am teaching MSc 6001. This is my intro to material science class, which you took. And you know, it is like famous for being too hard, but they have only begun to see how hard it can be. My grad students are getting the full wrath of like speed run of the major. We're going massively in depth. I did a whole lecture today on tensors and anisotropy and where the mathematical origins are of that for properties. It was a wild ride.
That sounds like a lot of fun.
I'm actually loving it. I taught that class 10 years ago, so it's fun to dive back into it. How about you? How's life going?
Oh, it's going all right. You know, getting back into it. I'm only taking one class this semester because I think this is my last one. It's a finite element analysis class, which I did a lot when I worked out in industry, but this is kind of my opportunity to go and really dig into the foundations of it and make sure I understand what's going on under the hood, which I didn't quite get as much of.
It's usually the other way around. You usually learn about a technique and you're like, well, that was something. And then you go and actually you see how it's used in the rest of the world. Like, dang, that was useful. I wish I'd have paid attention. Now you get to pay attention because you know how it's used.
Yeah, it's kind of nice to go the other way because I have the motivation for why I should care. So we're going through all these basic examples that are kind of annoying from a math perspective. And it's like, oh, this doesn't represent reality. And normally I'd be like, okay, what's my motivation for why I should be interested in this? But I know what the end result it is. I know what we're building towards, and that makes it easier for me.
Today we have an episode that encapsulates the past, present, and future of material science, and that is pyrometallurgy. That's right. We're going back to where we began. Pyrometallurgy is the field that takes the ore and process it till we get the metal. You started with the galena, you end up with the lead, right? And you do this for all the different metals because nowadays we benefit from having places like American Elements. Thank you, by the way. This episode is brought to us by American Elements, the world's manufacturer of advanced materials. You can check them out, AmericanElements.com. Now invent. And if you didn't have them, then how do you go about getting those metals from the earth to their final form?
Yeah, we were talking before this episode about how pyrometallurgy really is like the past, present, and future of material science.
That is material science.
Right? Pyrometallurgy is what first kind of opened up this door of saying, well, metals come in different forms and there's other things inside of them that you can use and they affect their properties. And then if we look at right now, pyrometallurgy is essential to meeting our demands for different metals, for all these technologies. And then we look into the future when natural abundance or easily accessible deposits of these metals are, and the ore they are contained within are starting to run out, right? We need to now be able to recycle all of these advanced alloys and metals and technologies that we've assembled. And pyrometallurgy will play a role there. So it really spans the continuum. It was there in the beginning and it's going to remain with us.
Yeah, and just a note on our future needs of metals. Listen to this quote. This blew my mind. This comes from an International Energy Forum quote, but they say, just to meet business as usual trends. So this is not like dramatic changes. Everyone's going to start driving EVs tomorrow or anything. We're going to need 115% more copper must be mined in the next 30 years than has been mined historically until now. All of humankind, we are approaching a real step change in our reliance on metals. Because think about it. In your phone listening to this right now is probably an iPhone or an Android or something chock full of all sorts of different metals. We can't just get away with aluminum and just steel. It's now a huge variety of different elements. If you look at like the footprint of the periodic table that we are using for technologies, it's just growing and growing and growing. So our reliance on this stuff, not just the breadth, but just the volume as well that we're going to need to increase is wild. It says here, to electrify the global vehicle fleet, we're going to have to bring into production 55% more new mines than would otherwise be needed. So obviously, Andrew, this is a pretty strong reason why we are talking to our material science and metallurgy students, because there's a job here in the future and there is a need to do this better. By the end of today's episode, we're going to touch on the things that have to change in this field, right? We're first going to describe pyrometallurgy and what it is, what it has been. But we're going to wrap up this episode saying what it needs to become to actually make this all work.
Yeah, that's right. So maybe we can go all the way back to the beginning and kind of talk a little bit about where this started and some of the early attempts at it. So it's a little unclear of when it maybe officially started as a field, but we found lots of artifacts that were composed of metal, pure metal, dating all the way back to 6000 BC, right? There are maces and various weapons that were found. They're made of copper. And so people were often speculating how they were able to get this. And it turns out they got lucky. They were able to find copper that was in a pure form, not necessarily in its ore. And they were able to figure out you can melt that and you can turn it into different things. There were mines in Israel, for example, that supplied this. And there's commentary historically on these weapons that were made of this.
And before even the weapons, right? When they first discovered it, they were smelting copper. Now, we're going to introduce smelting later, but they were basically just heating stuff up. And then they look, and in the fire, there's a little bit of a shiny, so a greenish blue stones. These are copper ores, leaving behind shiny little metallic beads. And they, without even realizing what they'd done, can you imagine being there in that moment, like looking down, being like, now what in the world is that, right? That sort of excitement. So this was not like, look, they don't have material science back then. They didn't understand these processes. It was very much trial and error and exploration that led to some of the first alloys. But that didn't mean that they stopped and weren't continually curious, right? This progressed from the very first sort of accidental metallic beads in the fireplace to understanding how to actually make, alloys. First copper, eventually bronze, eventually iron. This process sort of moved. And it was in response to the technological capacities that were opened up with materials with superior properties, meaning hardness, strength, right?
Yeah, it was kind of an interesting progression here where a lot of the metals actually enabled the processing of more advanced metals or more sophisticated, more like higher volume processing. They speculate that a lot of the early pyrometallurgy operations were sort of ad hoc. If they needed to do something, they would construct this wood pile, and then they would either do like a roasting or some sort of pyrometallurgical process on the wood pile, and then they would take it down. And because it was there wasn't that equipment or that understanding to create some sort of permanent fixture for doing this.
And some of this was secret. There's this story in modern day Syria in the ancient city of Ugarit. I don't know if I'm saying that right. But it has texts that refer to this so-called quote unquote secret of iron. Because imagine, like, this was like our secrets today are like nuclear weapons, for example, right? We don't necessarily want every country to have that because you lose your competitive advantage in warfare. It was no different back then. The secret for crafting and making these superior alloys was very guarded, right? Which is pretty cool to imagine how they were slowly learning this and then realizing the potential that it had, and so wanting to then keep that as an advantage for themselves.
Yeah, and there were lots of developments that ended up being furthered by alchemists, because they're very interested in changing things, right? They're searching for how to figure out to turn lead into gold. And so they thought, they found that, okay, maybe if we can refine things in a certain way, maybe we can get to that, or we can better understand different transformations. So they ended up doing a lot of development. And one of the key enablers was figuring out that if you inject air or oxygen onto a flame, it makes it burn hotter. This makes sense if you look at the equation and follow Le Chatelier's principle.
Yes.
Right. Okay.
Yeah. more reactants, get more products.
And so there's these early Egyptian hieroglyphics where they have people with little, they're not straws, but reeds or something, tubes, and they're literally just sitting there blowing on the flame to try to make it hotter, because they found that makes the process more efficient, or it makes it so that they can process new types of ore that they weren't able to with a wood burning fire.
Yeah, and obviously, if you've listened to our steel episode, number 1, our very first episode, go back and give it a listen. You can see this in all its gory detail. We saw the introduction of the blast furnace, for example, which was a sort of next evolution in this area, allowing you to get hotter, essentially. Once you can get hotter, you can smelt down the ores more efficiently to get the metals out of them. In fact, there's this cool story out of modern-day Belgium. There's a town called Liège, I think, and the blast furnace was so efficient, and it contributed so much to the wealth of that region, that there was an actual saying that said, as rich as a Walloon, which is obviously in reference to the prosperity of the Walloon ironworkers. So absolutely enabling technology as they learn to do pyrometallurgy better is really what we're seeing happen over time.
And so maybe now's a good time to talk about the different types of pyrometallurgy and why we would need this in the first place. So if we think about first the forms that many ores take, we're going to see a lot of oxides. So metals that are bonded to oxygen, as well as sulfides. And those inherently in that form are not necessarily castable or usable for, maybe initially making weaponry, but other sort of functional properties. And so we have interest of separating them and creating pure metals.
Yeah, I just took some notes. I was curious about that because they talk so much in the literature about the need to get rid of sulfides. I was curious, like, what happens if you don't? And it's fascinating, right? If you don't get rid of iron, sulfide in iron, you end up with iron sulfide, which is a brittle, it's basically a ceramic. And it's not just brittle, but it also leads to something called hot shortness. So when we do like hot rolling or hot forging, if that material is not going to be plastic, which is the whole reason we heat it up in the first place, then it's not going to function. And this causes that. It causes hot shortness or cracking and spallation in the hot form. With copper, you actually get lower conductivity, which is the primary use of copper nowadays. And getting copper sulfide as an impurity is going to reduce your conductivity, and it makes it more likely to corrode. In nickel, if you're left with nickel sulfide, you get nickel matte, which is brittle and also impacts toughness and corrosion, and on and on, whether it's lead sulfide with galena or zinc sulfide with sphalerite. It's just a real bugaboo in most of these industries. And so we need some sort of technological approach to get rid of sulfur, but not just sulfur. Like carbonates are another one they're often trying to get rid of, sometimes chlorites or silicate groups. There's lots of things that are present in the dirt that we mine up that you're going to have to separate out to just get the pure metal, whether that's iron or nickel or whatever else. Okay, so before we get into it, Andrew, let's pause and introduce the 4 key processes present in pyrometallurgy and the typical order in which you find them, although there's lots of variations, right? So those are as follows. You have the calcining, you have roasting, you have smelting, you have refining. What are those, Andrew? Let's start with calcining.
Yeah, so calcination is a thermal treatment where you will basically just heat something to a high temperature under limited oxygen. You're effectively trying to decompose things, right? So think about it from a thermodynamic standpoint. You know that at different temperatures, different phases or different compounds are going to be stable. So if you heat them up in an oxygen-starved environment, you're likely to result and cause things to decompose. And maybe that's what you want. And initially, this came from the desire to make calcium oxide.
That's right.
So that's where the name comes from. I remember when I first heard calcination, it was not in the context of this. And I was like, why is it called that?
Yeah, it makes sense, right?
It's really to go from calcium carbonate to calcium oxide and CO2.
Limestone into lime. And why is that important? Because once you have lime, you make concrete, right? So it's one of the key components to it. So yeah, that is calcination. By the way, I think it's important to point out that in the ceramics world, it's kind of the opposite approach. In ceramics, you're firing it in air, typically, not always, but typically this is done in air, but the underlying goal is kind of the same. Like you might have calcium carbonate, and what you really want out of that is the calcium, and it's going to react to form, maybe you're making a strontium titanate or whatever else, right? You need these things to react, and you start with precursors, which are very often nitrates or carbonates or sulfates, and you're burning off the parts that you don't want, and you're just being left with the metal oxides, typically in the ceramic world. This gets us part of the way there, right? Calcining doesn't get us all the way to pure metals, so we're not going to have to be able to use calcining alone. It's going to have to be in conjunction with some of these other techniques.
That's right, yeah. And there's lots of examples beyond that, as you've alluded to, such as the decomposition of hydrated minerals,
burning off water, right?
Devitrification.
Oh, yeah. So if it's glassy and you need it to be crystalline for the process, the good one in aluminum, right? In the process to make aluminum, future episode for sure, you have an aluminum hydroxide, and you have to burn off that hydroxide to get alumina. That's a calcination step.
Mm-hmm. Or even, shout out to our last episode, defluorination. If you have uranyl fluoride or this uranium fluoride compound, you can create uranium dioxide this way.
So another thing is that when they go about processing ores, when you're literally digging up stuff from the earth, there's almost always a comminution step where you're grinding it to get the right particle size for your process. Yeah. So now you have wet particles, and wet particles behave very differently in furnaces, and so you need to dry them out. So calcining sometimes is just drying things out. It's not as fancy as like decomposing. Sometimes it's just drying things out, although it's often both those things combined. And in the process, there's a significant volume reduction called decrepitation, right? So this is something that you can expect to see, is that your volume is going to decrease significantly. And there's some challenges, right? One of the common tools used here is a rotary drum, where you're literally just like rotate. Like, imagine like if you've seen like a cement roller, kind of like that, but now you're adding heat as well. The benefit is that this is cheap and easy to employ, but now you also have the possibility of impurities coming from the drum itself, so you can get iron impurities. When one of the big problems, the limitations there as well, was that it's happening in air. But as you started out saying with calcining, it's very often done outside of the presence of air. So that necessitated the creation of a new technique, which was steam dryers, right? Steam dryers, now you can have your ore in an enclosed vessel, but you have these pipes running through it, and you're passing hot steam through those. They're going to impart their heat to the stuff inside of it without necessarily exposing it so that there's a chemical reaction. So you're not oxidizing it. The benefit here is you're not oxidizing it, which is a big advantage. And then there's nowadays, there's other things. There's fluidized bed and flash dryers, but they're all kind of doing the same thing. You're driving off the species that you don't care about.
Your mention of steam reminds me of a fun fact I found while I was doing research for this. In alchemy, they have something known as philosophical calcination, which was said to occur when horns or hooves or other sorts of things like that were hung over boiling water or liquor until they had lost their mucilage and were easily reducible to powder. So it was sort of like an indirect calcination is how they thought about it.
Way cool. Oh, and you bring that up with bones, and in doing research for this episode, there was a bunch of ancient techniques where they were just trying stuff out, and they used the materials they had, and in many cases that was like animal bones. And there's this cool story about ancient Greek and Rome when they were doing processing, trying to get pure silver, and lead is an unfortunate byproduct oftentimes of that. So they're trying to get rid of the lead. So they would take these mixtures, lead and silver together. They'd put them in these shallow, porous dishes made of bone ash, which is literally just like the remains of burnt animal bones. And as they would fire it, then the oxidized lead would preferentially get absorbed into this bone ash, leaving behind the purified precious metal, which is so cool. So why bone ash? It has like a particularly high melting point, but more importantly, it has the right absorption properties. I assume because of the microstructure that's left behind after you burn it, but I'm not entirely sure. But very, very cool. They use this to purify silver to make it was highly prized for coinage, for luxury items. And these bone ash cupels can be found. Actually, these are still like artifacts that you can dig up and find, which is pretty rad.
Yeah, administrators were also very interested in this because they were trying to detect counterfeit currency, where people would basically try to change the composition and put more lead or other sorts of things in there or shave off certain amounts. So they could use this to basically separate the amount of silver, and then they could determine whether somebody had reduced its value or tried to extract some of it in some way. There was also a really interesting process that I came across called the Pattinson process. It was patented too by Hewley Pattinson in the 1830s. It was an improved method for separating silver from lead, and he basically exploited the fact that molten lead was the first metal to solidify between the two. And so what he ended up doing was he created this row of 13 iron pots that he would heat from below. And so within the central one, he'd have this lead-silver combination. He would heat this up until it was a bit molten, allow it to cool so some of the lead would solidify, and then he'd basically scoop that up with a ladle, and he'd move it over into one pot and then move the rest of it into the other, and he would slowly through this.
So this is like early refining, like a very painstaking
process.
Dude, that's awesome way to refine. Actually, that's a good segue. So we've talked about calcination. Eventually, we're going to get to refining. There's typically some steps in the middle, though. While calcination is often the first step, there's variations, of course. The second step is typically roasting. Tell me about roasting, Andrew.
Yeah, so roasting basically is going to consist of now deliberate gas-solid reactions, which can include things like oxidation, reduction, chlorination, sulfation, various other reactions. The main example you'll see is the conversion of copper sulfide, which occurs quite abundantly, to copper oxide. And the way that they did this in these massive roasting stacks, they would essentially pile wood in these just massive piles, and they'd put the copper sulfide on top of it, and they would ignite this. It turns out that this reaction is exothermic.
Yeah, so once you get it going.
Once you get it going, it will sustain it. And so I was looking into how big these actually were and how much they were processing, and it's pretty amazing. These heaps would be about 2 to 3 meters high into like a 15 by 30 meter area. And so these heaps would be about like 2,000 tons. And they would burn for, on the order of weeks to months, depending on the size. And these areas still exist. You can go to them where they had these massive heaps. And a lot of them are not necessarily habitable anymore because they burned in open air. So all of the byproducts were just condensed all around, or they just fell down into the soil.
In fact, so in this process, so what we're really taking advantage in roasting is the affinity for oxygen, because this is usually done in air. And if you're introducing oxygen and high temperatures for chemical reactions to take place, there's an affinity of oxygen to react with carbon and sulfur. Those are the two main ones. So if you have carbonate minerals or sulfate minerals, you're going to be able to have them react to form CO2 and SO2. And obviously, if you do this in large scale, like you're describing, you can end up with acid rain, right? That SO2 can react with water to form H2SO4. It literally can have acid rain as a byproduct of this. So when you read the history about this, it's fascinating. So I'm listening to, if you're not listening to our podcast, which should be your number one favorite, can I recommend a second, which is the History of Rome podcast? It's phenomenal. They're talking about the mining going on by the Romans in Rio Tinto, Spain. Rio Tinto, by the way, is now one of the world's large, mining companies. They took that same name. But it just talks about the massive scale mining and roasting that they were doing. And it says, the smoke from roasting was known to cause respiratory problems to the workers and even lots of the nearby inhabitants. So even going way back, Pliny the Elder, some of these early writers talked about the smoke and pollution caused by these metallurgical activities. So we've been doing this for a long time. There's stories about it coming out of, more modern days, in Wales, for example. There's whole portions of Wales that were impacted by this and many other countries. So roasting is necessary because you don't want those impurities in the final metal. If you listen to our Titanic episode, number 42, go back and give it a listen. You'll remember that the original idea about the ductile to brittle transition causing a big 60-foot gash or whatever it was is not the case. It was actually the rivets. The rivets had slag left over in them because they didn't completely purify the slag during the smelting process. We'll get to that next. And so that slag is full of iron sulfide, which is a brittle material. And so when they hit, they collided with the ice, they popped right off, which allowed it to sink the boat. So while roasting is typically involved with air because the oxygen in air is going to be reacting with things, it is, of course, possible to react it with anything during roasting. And sometimes they'll do that with chlorine. That's the case in titanium. Future episode coming on that, as well as other things, right? And there have been some innovations here. One of the big ones that is relevant to modern pyrometallurgy is the iron ore induration. So in the iron ore induration, this is a pre-step that's preparing it for the blast furnace where the smelting is going to take place. And essentially what you're doing is you're strengthening these pellets. They have to have the right consistent size and shape and strength to go smoothly through this blast furnace. And so this iron ore induration is a roasting heat treatment that allows you to do that. There's, of course, other examples, zinc sulfide converting to zinc oxide by blowing O2 basically over it, or the carbochlorination of titanium that turns titanium oxide into titanium chloride. Again, more on that later. That's the precursor that is used for modern titanium. So roasting is a pretty important step, but it's a precursor to the main event, which is smelting. Andrew, what's going on in smelting now?
So smelting is going to now use heat and some sort of reducing agent to decompose the oxide or the ore down into hopefully close to the pure metal, maybe some impurities. But largely the goal is to now separate those oxides from the pure elemental metal.
Yeah, your metal is almost always going to be in like a plus state, oxidation state, +2, +4, whatever it may be, because it's bonded with oxygen typically by the end of the calcining and roasting. So it needs to gain electrons. Reduction is gain electrons. So you need a reducing agent. In other words, something that gets oxidized such that your metal gets reduced. You have to have if you've taken an introductory thermal class or electrochemistry course, you know that you have to have a balance, right? If something gets oxidized, something gets reduced. Here we want the thing to get reduced. So something needs to be easily oxidized. So in the smelting process, you're going to introduce something. And unfortunately, right, that has traditionally been carbonaceous materials, right? They did wood for a long time. Then they discovered coke is a heck of a lot better. This is a refined version of coal, right? This is it's a carbon source, and that is going to allow you to react to form carbon monoxide or carbon dioxide, allowing the metal to pick up those electrons to become metal in its zero oxidation form. Now, you don't have to use carbon. There's nothing magic about carbon except that it's cheap and abundant and it works pretty well. Thermodynamically, it has a pretty strong driving force.
And CO2 is a gas, which automatically will separate itself.
Yeah, it makes separation pretty easy. But like you could do this with whatever you wanted. In fact, there's a big push towards using hydrogen, right? If you could react with hydrogen, now the hydrogen is going to get oxidized to form dihydrogen oxide, also known as water, right? H2O. And that would be awesome because now you don't have any carbon emissions. And why that's relevant is because the amount of CO2 that we are generating in metallurgy is bonkers, like absolutely bonkers. Here's just some numbers. This is from a 2022 article. They're pointing out that right now, the amount of minerals that we're producing, which remember is not nearly as much as we're going to need even in the near future, but even right now, we're making 1.5 billion tons a year of iron. And I just to put that, because that number means nothing to me, I had to like scale it. That's over 4,000 Empire State Buildings of weight of iron every single year that we're making. And there are, while that's the biggest, there's also major numbers coming out of aluminum and manganese and chromium and copper, right? So all of that together accounts for huge CO2 emissions. So if you look at the stats in 2021, as a planet, we emitted 36 billion metric tons of CO2. Half of that comes from heavy industry, transport, and mining, right? Heavy industry comes in at 24.2. Heavy industry is definitely using a lot of these minerals. So that's some fraction of that comes directly from our metallurgy. Transport, same thing. Mining alone is 8%. So all this to say that if we could find alternative reducing agents like hydrogen, if we could make that more feasible, this would have a serious impact on reducing CO2 emissions if that's something that you're passionate about, which I think we probably all should be worried about. I don't know if worried's the right word. We should be, as engineers, coming up with clever technological solutions to some of these grand challenges we face, including CO2 emissions.
Yeah, and just thinking about that in a cursory thought, that's very challenging. I think it would require a lot more temperature control to really pull off.
It's hard. And it also introduces other challenges you have to think about. If you're introducing hydrogen, how do you make sure you don't end up with embrittlement issues, for example? Or there's just new engineering challenges to deal with. Just like when they were doing the initial smelting processes and they had to figure out how they don't end up with slag left over in the mineral. So they had to come up with ways of separating the slag from now the molten purified metal, because if you don't, you get bad performing metals. We will probably have additional challenges in a similar vein as we move towards pyrometallurgy of the future.
Yeah, I mean, hot hydrogen is a big problem.
Let alone safety. Yeah, you're right.
And another important aspect of these, I think, is the addition of fluxes. Because
tell us about fluxes.
Yeah, it's not going to always just be the oxide. Other things just end up in these ores.
Like silica, right? Silicon is all over in these ores. How do you get rid of that?
And so fluxes are going to be things that they add to try to form a slag and to be kind of binding agents here to try to collect up all of these things and catalyze certain reactions such that those don't end up within the final metal product. Best
case scenario, your flux is also easily separable. It floats, it sinks, typically floats, right? Such that you can skim off the top. Like if you've ever seen like these old, I think it's like some old movie where they show you blacksmithing, they're scraping off that nasty frothy slop. That's the slag, right? That is, they've intentionally or intentionally like added a flux to it, which is usually forming ionic compounds. It's forming salts or oxides, which are then going to float to the top of your molten metal, hopefully, because of their lower density, typically significantly lower because of the oxygen presence. But yeah, that's something that we're going to have to do. In the smelting world, this can be done in the gas phase, as you mentioned with like CO2. It can also be done in the liquid phase, right? And there's some real advantages to doing this in the liquid phase. For one, it increases your kinetics and diffusion. Think back to your intro to material science class. Diffusion in solids is slow because you're hopping from spot to spot, either sites or interstitials. It's slow. But if things are molten, your diffusivity is orders of magnitude higher. So that no wonder that kinetics are a lot faster. The second thing that it does is it facilitates this physical separation. Maybe it floats to the top, for example. And then third is you get better heat transfer inside the reactor. And this is just going to give you a more homogeneous temperature profile. And as we know, so many processes are thermally dictated. You wouldn't want part of your giant vat to be at a different temperature than another if you can help it, because then you might get spatial inhomogeneities, which is not going to be ideal.
Yeah, and we really benefit from that, having electric furnaces now where we can control those sorts of things. Imagine trying to do this back then where they were using fire or coal or some sort of burning method. I was looking at some
your heat source is just underneath. Now we can put heating elements all around this thing to sort of have individual or tailored control of the overall temperature profile. I can't imagine what they did. Like when you see the amazing tools that came out of, take like the samurai swords we see, or like Damascus steel, or some of these amazing metalworking, and then you think the tools that they were working with, it's unreal. It's unreal.
Yeah, I was looking at some of these early furnaces, like the reverberatory furnace and such, where they started to realize that they need to separate their heat source because they were contaminating their metal with it. But that becomes a new challenge because all of a sudden it's like, well, how do you separate that sufficiently while transferring heat evenly and uniformly? And so they came with these like rotating mechanisms. They started to realize that they need a lot more air injection, so they started building these next streams and such so they could get bellows and such that were constantly pumping.
So you're dead on that electric arc furnaces have become very, very important. And today, if you look at how we smelt things, chromite smelting, this is iron and chrome smelting, silica smelting, so this is iron and silica, iron nickel, production of laterites, metal recovery from slag, platinum group metals, all of these extensively use electric arc furnaces. And one of the challenges, well, one of the benefits of electric arc furnaces is the separation of heat to different regions so you can more accurately control it. But one of the downsides or the challenge that to come up with is now your reducing agent isn't your heating agent. So you have to still have a reducing agent, right? The electrochemistry still has to happen. So they typically have used graphite electrodes, which are either pre-baked or baked during the process. And we'll get into that, I think, in a future episode. But the point is these are injected into your mix and they get consumed during this furnace operation to produce the gaseous carbon monoxide or dioxide, whatever's happening, right? You can use other things. You can use coke and other stuff, but it has now become very common to use these electrodes. And there's an active area. Just this year, we submitted a grant, my research group, trying to work on inert cathodes, right? If we're not trying to consume massive amounts of carbon and emit more CO2, what if you could still get that electrochemically or in other ways where you don't have the carbon emissions, essentially? This would be a big breakthrough for aluminum and many other processes if we could pull this off.
So maybe before we leave smelting, we should talk about something that sits at the intersection between roasting and smelting, and that's flash smelting.
Yeah, tell us about
which
that.
is basically an idea to combine roasting and melting into one furnace. The idea here is that you can take fine dried mineral particles and various fluxes, and you can basically just eject them into a heating gas stream. And after ignition, as we mentioned with the roasting process, especially with things like sulfides, those exothermically react, they'll start to become self-sustaining. And because now you have this in a small particle size, the reactions end up being quite rapid. And so
cool.
flash sintering has been a really important development that is not only more energy efficient, it's like 50% of the energy of previous roasting methods, but it's also quite effective. And it extends beyond things for copper. For example, nickel is often found with iron, and so that creates this additional separation step. But flash smelting actually does a pretty good job of promoting that separation and giving you nickel that is more nickel than the other potential contaminants. But it's also a really complicated process. And if you read the literature or various books on this, they still note that a lot of the designs of these are more art than science.
Oh, really?
Well, I mean, think about the complicated interactions that are happening there. You have turbulent fluid flow, you have convective heat transfer and mass transfer, chemical reactions, radiative heat transfer. It's very complicated. And so there's been a lot of work recently in using computational fluid dynamics and other things to try to design these processes to be more efficient, as opposed to just, this is how we ended up designing it. It kind of works. Here's some intuitive heuristics for how we should design this.
And it's not that old of a technique. Like, it was developed in the 40s, basically. That's like a couple generations ago. And it was originally not accepted necessarily. There's a lot of skepticism. It took time for its efficiency sort of win over skeptics and demonstrate it. And then obviously the reduced energy consumption compared to traditional reverberatory smelting has now made it a very popular tool used today.
Okay, so we've got something that's ostensibly the pure elemental metal, but there's still more steps. It's not going to necessarily be fully pure, and maybe there are things we want to add to it. So what's the final step in this process?
So the last thing we got to do is refine, right? These processes are pretty dirty up until now. And obviously depends on your starting minerals. That is going to be the biggest dictator of the purity. But these processes are also imperfect. And what comes out is not necessarily something that American Elements is ready to sell us, right? You have to go through a series of refinements, especially if you're making really high, research grade stuff where you don't just want like 99% tin, it's got to be 9.999 or whatever, right? It becomes more challenging. And so there are a number of techniques whereby we can refine them. Take copper, right? Copper is one that I'm familiar with because we have Rio Tinto in our backyard turning out huge amounts of copper here in Salt Lake City. And that's an electro-refining process. That's not a pyrometallurgy technique. Instead, they are carefully introducing, the as-cast copper ingots, as it were, which has impurities. It has things like tellurium, for example, and other stuff. I think it has mercury and other things like that in it. But what they do is they have a counter electrode, and they very, very carefully control both the electrolyte solution and the voltages is the most important, such that you preferentially get the dissolution of copper and then replating of copper on the other electrode, which now it's pure copper getting plated. And the other things, if you have your window controlled and your electrolyte solution controlled properly, they will not plate out. They will maybe fall down. They'll be discarded or they'll be left in the solution, but you don't want them plating out. Sometimes this happens in one shot. In other cases, I think it's an iterative process, but this is one way that you can go about refining to get, in that case, pure copper. What are some other approaches they take to getting refinement, Andrew?
Yeah, another one that I'm familiar with is this idea of zone refining, which is really cool. So you have some sort of bar or length of material, and you can locally heat it up. And there's differences in solubility of all of these different materials. And so if you heat it up in a very local area and you slowly move this heating zone across the bar, the elements that are much more soluble want to stay in that melted, sort of molten solution. And so what gets left behind is the pure metal.
Yeah, picture like a phase diagram. I think most of our students have seen like a binary eutectic. So if you go above the eutectic temperature, if you heat something up, typically that solubility window goes towards the axis. So there's not as much solubility up here. And that means if there's not solubility, you mostly have the pure solid plus the liquid. So the idea is that you're moving this liquid region slowly through the bar, and that's accumulating your impurities. And you can do multiple passes and push these out. So I've seen this for single crystal growth and other things like that as a way to purify. So for silicon, right, you need to get that very, very high purity. That's one way that they do zone refining of that. Very, very cool technique.
Yeah, I've seen it used for as a way to try to extract the waste in nuclear fuel rods as well. Because after they're used, you have all this other sort of nonsense in there that they want to separate. And there's been some research into whether or not you can zone refine these.
So we've been talking about these things as if they're like completely separate processes, but sometimes these are very much tied to one another. For example, it says here, it should be highlighted that the refining units typically take advantage of the already hot and molten metal to be refined, right? So you just finished smelting it. You can use that same sort of process to do the refining without necessarily having to heat and melt and go through that whole energy requirements again. And some of the processes that they use kind of sound like the smelting process, where maybe you're adding something that's going to form a slag, which will float, and then you can scoop it out and go about purifying it.
Yeah, or they'll just take advantage of different melting points or densities. For example, sometimes if something has a particularly low melting point, you can just heat it to that melting point on like a sloped surface, and the metal of interest will melt and will go down the slope and collect, whereas heavier things will remain there in either a solid form or others. Or there's like a distillation process too, where you can heat these up really high, and certain things are much more volatile, and so those will be emitted in a gas phase where they can be collected, condensed, and turned back into something usable.
Okay, so you are all now experts in the fundamentals of pyrometallurgy. Congratulations. But I'm sad to say that we're not going to do it the way that we've always done it going forward. We can't. Let's just highlight a couple of the problems with the way that we do it right now. Maybe first and foremost is that the whole reason that we've been doing it the way we have is because it's been cheap. It takes advantage of cheap and abundant, typically carbonaceous resources. Those are going to be our fossil fuels for both the heating sources, but also for the coke, which is in many cases, iron in particular, has dominated as the reducing agent, right? Then there's also the heating sources, which are typically also going to be coal-fired power plant, it provides electricity or something. But there's other problems, right? During the calcination, roasting, smelting, refining, there's clearly a lot of byproducts. I just said that copper generates mercury as a byproduct, right? What are you going to do with that? Or during the roasting, okay, so now you produce a bunch of SO2 gas. What are you going to do with that? The output streams of these like the byproduct reactants, for one thing, they are higher residual energy and content. Like there's untapped resources there, like we're just wasting them. And another, they can be hazardous, right? And so that involves typically gas scrubbing or capture strategies, including CO2. We're increasingly talking about CO2. You remember our previous episode on that. So those are a couple of reasons. Anything else, Andrew?
Yeah, these are also really energy intensive.
Yeah, 1,500 degrees Celsius.
Yeah, even some are even
hotter.
Yeah, looking at some of the really early furnaces that came around in the 20th century, mid-20th century, some of these were using, town scale energy supplies just to operate, and so that has a huge energy draw versus maybe the product that you're producing. So, right, if you have this idea that you're going to make this more environmentally friendly, well, that incurs a cost. And then all of a sudden you have to probably increase the amount of energy that you're expending. And so, there's trade-offs here that are quite difficult to balance.
So looking forward, and we're definitely going to do a couple episodes on this, but there's going to be alternatives that we can think about. For example, if you're not going to use coke, what are you going to use? Well, there are biofuels. There is biochar, in particular with coke there. There is hydrogen and ammonia, using these as the reducing agents in different pyrometallurgical units. There's also the notion, which is going to be increasingly important, of managing recycled waste streams. So what happens in the future where urban junk piles are the new mine source, right? The sort of low barrier to entry minerals that we can dig out of the earth are all used up. And the resources that we need are now in our old devices sitting in the dump heap. How are we going to go about taking waste streams and converting those now to a primary metal resource is going to be a very important area, particularly with lithium-ion batteries and a few critical technologies where we just don't have enough of that mineral. And then lastly, different reduction agents, hydrogen or metalloreduction or inert anode electrometallurgy. These are all going to be things that are going to play an important role, which is why we're training people like you to go out there and help us find solutions to some of these things.
Yeah, as well as some developments of new extractive techniques. A lot of interest in plasma arc furnaces, which are smaller. They can operate at really high temperatures and give you a lot more control. And being able to go to high temperatures allows you to, one, work with certain metals that couldn't be worked with before, or at least easily worked with in a much more energy efficient way, right? Try melting tungsten, at least easily in a way that's energy efficient.
Yeah. Good luck.
Or even developments in terms of how we inject air or how we inject the fluxes into this. There's this emergence of these top submerged lance furnaces where they have basically a tube coming down into the slag, into the top of the molten region, and from that they can inject air at different velocities to create turbulence so that it mixes better, as well as to control a number of different processes there, and that has opened up more efficiency and opened up more flexibility as we have to deal with more complicated ore streams as well, and in a much more compact design too. And I did a lot of research as well on this. How do we start to think about recycling lithium-ion batteries, and what role will pyrometallurgy play in that? And it's very complicated, right? The cathodes in particular are pretty challenging, being like a lithium, cobalt, manganese, nickel compound. Converting them to oxides works, but it's still a bit of a nasty process. And so another really interesting technology that's coming about is the use of microwave heating, which we talked about way back in an early episode.
Dude.
Yeah, it was very early on. But this ends up being very energy efficient, and you can get to pretty high temperature. And it turns out that the materials within lithium-ion batteries are very susceptible to microwaves, and so the heating actually increases. And they've been able to show through subsequent leaching processes of the microwaved product that they can get up to 97% extraction of some of these.
Pretty cool. Pretty cool. I don't think I gave enough credit to our pyrometallurgist friends. Our department was a material science and engineering department, and in 2019, up until 2019, there was a separate metallurgy department here at the University of Utah and a different college. Long story, don't get into it. But I don't think I realized what they did. I thought they just did like material science, but only on metals. And then when I met them and met the people where they're working, a ton of them did this so-called extractive metallurgy. And I was like, what is that? And over the years, I've learned that it is exactly the stuff we're talking about here. It's a focus on the process, a little more than the final product, I would say. But it's fascinating, and it's no less important or critical. Just one last stat I'll throw at you. A single electric vehicle, the battery weighs about 1,000 pounds, but to get that involves digging, moving, and processing 500,000 pounds of raw material. So it just shows the scale and the magnitude of the problem that these folks are trying to solve. So stay tuned for future episodes.
Yeah, and before we go, it's worth mentioning how important computational chemistry and physics were in really revolutionizing this field, right? Without things like the NIST GenF tables, and without thermochemistry of steelmaking and various other compendiums that collected all of this thermodynamic and chemistry knowledge, it probably wouldn't have made it as far as it did. And many of the modern efficiencies and cost reductions and energy reductions have really come about because of these tools. And so we can't say enough about their value in accelerating this field. And it's still very much an area of open research. And we can't wait to see what happens next.
Okay. Thank you for joining us. A fun episode to talk about. Obviously, American Elements is a sponsor, but we also want to point out Materials Today. They have been an amazing sponsor for a very long time. Thanks the Materials Today, we can keep producing this show. We hope that you'll check out materialstoday.com to stay update with the latest happenings in the material science field. Read some of their great articles. They are a high impact publisher, which means they get really interesting articles there. People that are really pushing the boundary. I find myself reading there quite often. So check out elsevier.com, materialstoday.com, and check out their books, conferences, and other programs. And lastly, we're always grateful for the other things that make the show possible, like the music. You can find Alphabot and Kolobyte on iTunes and elsewhere. So we'd appreciate if you check them out. And we would always love if you would give us a review. That will teach the algorithm that other people should also listen to this. So give us a hand. You can actually leave us comments or reviews, iTunes, Spotify, YouTube, wherever you listen to your podcast, we are found there. And if not, tell us and we will get there. And lastly, just interact with us directly. If you got an idea for an episode, want to shoot us an email, we are materialism.podcast@gmail.com, or you can find us at materialism.podcast on Instagram and chat with us. Okay, thanks so much.
Yep.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.